All right, everybody, welcome back to the next video. I am back from vacation early because my baby was not having it, so we had to come home. And so I'm back with another video. We're going to talk today about enhanced elliptic curves. This is going to be the first stage in our journey towards discussing modular curves. So what's an enhanced elliptic curve for gamma 0 n? It's an ordered pair E comma C, where E is a complex elliptic curve and C is a cyclic subgroup of E of order n. Remember, E is an abelian group under addition, and so this makes sense. We can have cyclic subgroups of E, specifically of the complex points of E. We say two such pairs, let's say EC and E prime C prime are equivalent, and we'll write EC tilde E prime C prime when that happens, if some C isomorphism from E to E prime takes C to C prime. Very simple, right? In other words, we take the level n structure of E to the level n structure of E prime. We're going to write S sub 0 of n to be the set of all enhanced elliptic curves for gamma 0 n mod C isomorphism. So in other words, it's the set of all C isomorphism, or I guess you could say it's the set of all equivalence classes of enhanced elliptic curves for gamma 0 n. Its elements will be denoted by bracket EC. So individual enhanced elliptic curves are specific ordered pairs, but elements of S0n are equivalence classes of these enhanced elliptic curves. Okay, how about for gamma 1 of n? What do enhanced elliptic curves look like? Well, for gamma 1 of n, the correct notion of an enhanced elliptic curve is an ordered pair E comma Q, where Q is now a point on E of exact order n. So no longer are we looking at a subgroup of E of order n, we're looking at a point of order n, and it does have to be exact order n, okay? So we're going to say two such pairs are equivalent, writing E comma P tilde E prime comma P tilde in the usual way. If some C isomorphism from E to E prime, you guessed it, takes P to P prime. And we'll write S1 of n to be the set of all enhanced elliptic curves for gamma 1 of n mod equivalence. And we'll denote elements of S1 of n by bracket E comma Q. So those will be equivalence classes of enhanced elliptic curves for gamma 1 of n. Okay, how about for gamma of n? So an enhanced elliptic curve for gamma of n is an ordered pair E comma parentheses P comma Q. Okay, and what's this P comma Q? P comma Q, it's a pair of points on E generating the n torsion E bracket n. Remember, the n torsion is abstractly as a group isomorphic to Z mod NZ cross Z mod NZ. And so essentially what we're doing is we're taking a basis for the n torsion, P comma Q, and we're also going to require that the Weil pairing E sub n of PQ is e to the 2 pi I over n. It's the usual primitive nth root of unity. Equivalence is defined like in the previous two cases. You're looking for a C isomorphism going from E to E prime, sending basis to basis. And we'll write S of n to be the set of all enhanced elliptic curves for gamma of n mod equivalence. And we'll denote its elements by bracket E comma parentheses P comma Q. Okay? And so what's going on here? Each of these S spaces, S0 of n, S1 of n, and S of n, is a moduli space, what we call a moduli space of isomorphism classes of complex elliptic curves. And each of those curves has been equipped with some kind of n torsion data, whether it's a cyclic subgroup of order n, a point of order n, a basis for n torsion, something like that. So a moduli space is something that, like in itself, is an interesting geometric space, but its points correspond to or parameterize various types of geometric objects equipped with extra data. Okay, and so when n equals 1, all three spaces above, S0 of 1, S1 of 1, and S of 1, they're all just the same. They're all isomorphism classes of complex elliptic curves, mod C isomorphism. Okay. So S1 is just like its points are isomorphism classes of complex elliptic curves, okay, over C. All right. So more generally, if I take a congruent subgroup gamma for SL2Z acting on the upper half plane H on the left in the usual way, then the curve Y sub gamma is the quotient of the space of orbits under gamma. So Y sub gamma, it's by definition gamma and then kind of this slash H here, but this is notation from your algebra class for the orbit space of this action, right? So it's the set of all gamma tau for tau and H. Okay, if you've seen my series of talks on the congruent number problem, you should think of these Y sub gammas as fundamental domains for the various subgroups gamma, I guess I should say, after we identify appropriately boundary points on these fundamental domains. However, we have not yet compactified them. Okay, so they're non-compactified fundamental domains for congruent subgroups of SL2Z. Okay, these y sub gammas here, they're usually called modular curves or open modular curves. And specifically, when my gamma is either gamma 0 of n, gamma 1 of n, or gamma of n, I have special notation for y sub gamma in that case. In the case that gamma is gamma 0 n, I'll write y sub gamma as just y sub 0 of n. In the case gamma is just gamma 1 of n, I'll write y sub 1 of n for y sub gamma. In the case gamma is gamma of n, I'll write y of n instead of y sub gamma. Okay, so these are the three kind of special open modular curves that we'll deal with. So here's the big theorem from today. First of all, let L sub tau be the lattice generated by tau in the upper half plane and 1. Okay, and let E sub tau be C mod the lattice, the associated elliptic curve to that lattice. Okay, so theorem, here's the first part of the theorem. Let n be a natural number. The moduli space for gamma 0 of n is S sub 0 of n, of course, by definition, but what is it? Like, what are the points in there? Well, it's the set of all equivalence classes that take the following form. E sub tau, comma, a group generated by 1 over n plus the lattice. So in other words, the coset of 1 over n for tau and h. So you can boil down the moduli space for gamma 0 of n to just consist of equivalence classes that take this very specialized form. Your generic elliptic curve attached to a tau and h, and then your generic subgroup of cyclic subgroup of order n, just generated by a typical 1 over n, coset of 1 over n plus your lattice. Okay. Now, 2 points in S sub 0 n are equal if and only if their tau values have the same gamma 0 of n orbit. In other words, there is a bijection, which I'll call psi sub 0, from S sub 0 of n to y sub 0 of n. So you can think of the orbit space of the action of gamma 0 n on the upper half plane. You can think of that as just S sub 0 of n, which is fantastic. Okay, and here's the map. It sends an elliptic curve, C over L tau, comma, 1 over n plus L tau, that cyclic subgroup of order n. It just sends it to the orbit of tau under gamma 0 of n, of course. Right? So this is a bijection. That's what's going on. How about for gamma 1 of n? Well, it's from here on out, it won't be too surprising, anything I say. The moduli space for gamma 1 of n is S1 of n. Okay, what is that ordinarily? That's the set of all enhanced elliptic curves. For gamma 1 of n, mod equivalence, it turns out you can boil that down to the following set. It's the set of all, I guess you could say, equivalence classes, E sub tau, comma, 1 over n plus L sub tau. So it's almost the same as the moduli space for gamma 0 of n. There's just no bracket here. And that's because I don't want to consider subgroups of order n on E tau. I want to consider points of order n on E tau. Okay, and 2 points in S1 of n are equal if and only if their tau values have the same gamma sub 1 of n orbit, of course. And so in other words, there's a bijection, psi sub 1, I'll call it, from S1 of n to Y1 of n. And it sends an element of S1 of n, so a typical C mod L sub tau, comma 1 over n plus L tau to the orbit of tau under gamma 1 of n. Okay, how about for gamma of n? The moduli space for gamma of n is S of n, and it can be boiled down to the following. It's the set of all pairs or equivalence classes, if you like, E sub tau, comma, tau over n plus L tau, comma, 1 over n plus L tau. So the basic claim here is like, for E sub tau, a basis for the n torsion is tau over n and 1 over n. In reality, it's their cosets, of course, because E sub tau is C mod L sub tau, right? But I'm being loose with my language. You can think of tau over n and 1 over n as being sort of a basis for the n torsion of E sub tau. Okay, and of course, 2 points here. You guessed it, they're going to be equal if and only if their tau values have the same gamma n orbit. In other words, there's a bijection, which I'll call psi from S of n to Y of n, given by C mod L tau, comma tau over n plus L tau, comma 1 over n plus L tau gets mapped to the orbit of tau under gamma of n. All of this is proven in Diamond and Sherman chapter 1. So what's going on here is that orbit spaces of various special congruent subgroups of SL2Z can be thought of as spaces which actually parameterize complex elliptic curves, mod equivalents, each equipped with some piece of end torsion data, which is very, very interesting. This is one of the first and most shocking kind of initial connections you see between elliptic curves and modular forms. How these subgroups of SL2Z happen to create these nice curves that parameterize complex elliptic curves with end torsion data is pretty remarkable, even though it's, in the grand scheme of things, a relatively trivial result compared to some of the things we'll see. Okay, so wrapping up, if I specialize to n equals 1, what I see is that the space of isomorphism classes of complex elliptic curves parameterizes the curve y of 1, which is just SL2Z itself acting on H. Okay, a fundamental, which is, if this notation again, is just the orbit space of SL2Z acting on H. It's a fundamental domain with sides identified but not yet compactified. Okay, similar stuff. Okay, so Y1, this very special modular curve, it parameterizes isomorphism classes of complex elliptic curves over C, the complex numbers. Okay, so next time we'll start looking at how to define compactified modular curves over C. And so thanks for watching, and I'll see you then.